Hello everyone. In this video, we're going to be solving an interesting exponential equation. I guess we could call this problem homemade because I haven't seen this problem anywhere else, and I kind of thought about it, but maybe someone else thought about the same thing, and if you do know, just let me know. So anyways, we have x to the power ln x equals e to the power e. And I know what you're thinking. You're thinking, oh, this is way too easy, I can just plug it in. But that's not the point. Obviously, you can always guess and check, but we're going to do a little bit more than that. So we're going to analyze this function a little bit. We're going to do a couple of different things. We're going to look at a graph, and hopefully it'll be helpful. All right, let's get started. So for these kinds of questions, especially when there's a variable in the exponent, and we kind of have like a tower here, sort of. And it's not x to the power x, but the highest exponent is different. But logging both sides will be helpful. And since we have ln x here, I'd like to use natural log, which is ln. It's just backwards, right? So let's go ahead and ln both sides. And obviously the presence of e, not just e, but two e's, also give us a clue about using natural logs. I mean, you can use log x, but, or just log both sides. It's just going to be harder. So what happens when you log both sides? The exponent, you can bring it down. But what is the exponent here? We have two exponents. Well, this is the exponent we're talking about, right? What is the exponent for the base x here? And what is the exponent for e? It's e. So we're going to move those to the front. Let's go ahead and do that. You know that we have a power property of logs, which is super duper helpful. So if you have ln e a to the power b, that can be written as b times ln a. And how do you prove that? By using the definition of logs. It's very easy to prove. So after we move the exponents, we get the following. X to the power ln x, not x ln x, obviously. It is x to the power ln x, which is the exponent, times the base, which is ln x, equals e times ln e. I just wrote everything down. Now I'm going to simplify it. ln e, now remember what is ln for those of you who are not familiar with ln. Ln x means log x with base e. So since the base is e here, ln e is going to be log e with base e, which is equivalent to 1. So this is 1. I don't have to worry about it. Just cross it out. We end up with e on the right-hand side, which is fairly simple, right? But on the left-hand side, we get something, it's not too complicated, it's okay. But we still have an exponent. So what does that tell you? Whenever you have a variable term in the exponent, log both sides. And we'll continue with natural log, okay? So I'm gonna natural log this side, and I'm gonna natural log this side. But natural log of e is just 1. We just talked about it, right? So, and here what happens is the product property applies. What is the product property? The product property is ln ab, or any other log, doesn't matter, can be written as ln a plus ln b. Again, this can be proven using the definition of logs or by substitution. So we can write this as ln x to the power ln x plus ln of ln x. So it's kind of like a double ln, okay? Equals ln e, which is 1. Awesome. Well, I don't know if it's awesome, but it's good. Don't worry, it's going to get better, by the way. So what we're going to do next is, again, using properties of logs. We talked about it several times. We can move this to the front. Let's do it, and we get something that should be familiar to you, ln x times ln x, hopefully, right? Plus ln of ln x equals 1. So that's kind of like an interesting equation, don't you think? And I didn't know that I was going to encounter something like this when I kind of thought about this problem. You know how I came up with this problem? Let me not tell you. If I remember, I'll tell you later, because that would kind of give away my, thought. So I don't want to give away that. That's why let me not talk about it right now. Hopefully I'll remember to talk about it. Anyways, so we get this interesting equation, but ln x times ln x is just that thing squared, right? A times A is A squared. So basic algebra. So this is ln x squared plus ln x equals 1. Now, here's the thing. Suppose you were integrating this expression and you have ln x squared plus ln of ln x or something like that, something similar to this. It doesn't have to be the exact same thing. But when you see ln x several times, what does that tell you? That tells you to use substitution, doesn't it? Well, it should. So this is a good candidate, and you know substitution is powerful. Let's go ahead and call this t. I don't know why, but I like t. So that tells us the following: t squared plus ln t equals 1. You see, that's the power of substitution, in general power of math. And the beauty of math is you can simplify something by using just substitution. Okay, this looks simpler, obviously, but after solving it, we kind of have to go back to our original. But this is easier. Don't you think this problem is a lot easier than what we started with, right? Well, except for guessing. I know you probably already guessed. Anyway, so what am I going to do with this equation? Well, I can kind of think about it this way. Let me give you one idea, and then I'll jump to another idea. T squared is an increasing function. ln t is an increasing function. The sum of two increasing functions is increasing because the derivative of a sum is the sum of derivatives, if you think about the meaning of the first derivative on an interval. So we have an increasing function on the left-hand side and one a constant or a horizontal line on the right-hand side. And they can only intersect at what? We have an increasing function and a horizontal line. They can only intersect at a single point. Obviously, that's not the graph for our function. That's just a random curve. Our function is going to be much, much nicer than that. And guess what? It's going to have a parabolic property and also a logarithmic property. I don't know. I haven't graphed it, but I'll show you another graph, not this one. So what can I do with this? I can isolate ln t. Let's do it. Why? I'll tell you why in a little bit. Because I know the graph of ln t and I know the graph of 1 minus t squared. Why? One of them is a parabola, the other one is the log function. Oh, come on. You should know these basic graphs. If not, maybe in one video we can talk about it. How do you graph quadratics? How do you graph cubics in general? What are some of the what was the term? Parent functions. Yes, it wasn't the family, but it was the parents. Anyways, parent functions, right? Like you have something like y equals x to the power 2, or you can talk about y equals ax squared, so on and so forth. Anyways, so you should know that the log function looks like this, sort of, right? So it's concave down because its second derivative is negative on that interval. It's only defined for positive values because t is real, so on and so forth. An increasing function, 1 minus t squared is a decreasing function. Why? Because as t increases, 1 minus t squared decreases. And guess what? This is a parabola, so I can graph it very easily. And I'll show you the graph at the end, so let me not graph it right now. Let's go ahead and do the following. Since we have an increasing function on the left-hand side and a decreasing function on the right-hand side, it's weird that I wrote it backwards, sort of, then there's only going to be a single introduction point. Just like this one. I mean, it's the same idea. We just switch things around. So how do you do this? Let's go ahead and take a look at the derivatives, right? Well, we don't need to. The derivatives, because we already know one is decreasing, one is increasing. So at this point, you can go ahead and guess. And guess what? We can set both of these equal to 0. That's the first thing I would try. If I'm trying to solve a non-standard equation, I will always set both equal to 0, see if that's a solution, and it happens to be. Why? Because ln t equals 0 implies t equals 1. I'm lucky today, right? 1 minus t squared equals 0 implies t equals 1 or t equals negative 1. I don't care about negative 1 because t already works. Okay, t equals 1 is a solution. Awesome, awesome. But t equals 1 means what? T is ln x, so t equals 1 equals ln x. That means x equals e. Now, before I show you the graph, I could pretty much tell you how I came up with this problem. I remembered, yay, because I was telling you I promised to do that. Okay, so here's how I came up with this problem. I started by stacking up these things like, okay, I'm going to start with x and then stack up x and another ln x. You could also do the following, x to the power ln x to the power x, or you could put another ln x, or you could put an x, whatever. And then I just plug it in. Since I have ln x, I thought to plug in x equals e. When I did, I got e to the ln e. Ln e is 1. E to the 1 becomes e to the e. And there you go. Here's how I came up with the problem. Easy piece of cake. So x equals e is a solution. And let's go ahead and take a look at the graph real quick and we'll finish up. Yay. Okay, so we have this parabola, f of t equals 1 minus t squared. And then we have the g of t, which is ln t. As you can see, they intersect at a single point. But our graph has two pieces. Why did I do the dotted line for this guy here? Because that is where t is negative. But I don't care about that because ln is only defined for positive t's. Therefore, if there's an intersection point, it's going to be for t greater than 0. That's why the dotted line doesn't matter. And as you can see here, they're only going to intersect at a single point. If both branches worked, would they intersect at another point? No, because the y-axis is going to act like a wall. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.